Hi everyone, myself Anand, and today in this video I will be explaining you the problem rotated sorted array from the rotated sorted array search problem from the interview bit platform. And first of all, let's read the problem. So the problem says that given an array of integers a of size n and an integer b, array a is rotated at some pivot unknown to you beforehand. Okay, and we are also given a target B to search, and if the target B is found, we have to return its index, otherwise return -1. So let us first understand what the problem says. The problem says that we are given a sorted array which is rotated, right? Which is rotated by some units. For example, let's say the the sorted array initially was like this, like 10, then 12, then let's say 18, and then let's say 15, or maybe let's say 19. Okay, so if you just rotate it by, let's say, 2 units, it will become 2 units to the right, it will become 19, or let's say it will become 15, then 19, then 10, then 12, and then 18. So if you just rotate it by 2 units to the right, it will become 15, 19, 10, 12, and 18, right? And let's say we have to search some value. Let's say that value is 10. Okay, so let's say this was my initial array, and this was my initial array, and let's say I have to search some value b is equal to 10. So obviously the value 10 is present at index 2, so the answer will be 2 in that case, and this array is 0 based indexed, right? So let's take example from this. Let's say this example and try to analyze it. So yeah, so yeah, let's take this example. This is 45670 123. As you can see, this array like 0 1 2 3, then 4 5 6 7. Okay, so as you can see that the initial array was something like this. It was like 0 1 2 3 4 5 6 and 7. And if you just rotate it by, if you just rotate by 4 units, right, 4 units to the right, units to right, then you will get something like this, right? Like this 0 will go 4 units right, right? So it will come here, and similarly all the elements get shifted by 4 units to the right, and the last element comes to the front and similarly gets shifted just like a cyclic array, right? And so here the element 4 is present at the first index, so we will return 1. This is what the problem says, and if b is not present in my array, then I need to return -1. So, so once understood this problem, now let's try to think of how we can approach it. So one way of approaching it is to just search through the entire array one by one, checking each element from left to right, and once we found some element which is equal to b, we will just return it. So a naive approach, okay, so we zoom it a bit. Okay, so in a naive approach will be to just go on each index from left to right, taking each element one by one, right? And once you found some element which is equal to b, you need to just return it, but the time complexity of that will be order of n, right? And the space complexity will be order of 1. Okay, so the naive approach is just what we call as linear search, right? You just search linearly from left to right. Once you found any element which is equal to b, you just return it. Okay, but the time complexity will be order of n, and the memory space complexity will be O of 1. but can we optimize it? Can the time complexity be reduced? uh, since you see the array is not completely sorted, but it is a rotated form of a sorted array, right? So if the array were sorted, we could have applied binary search and solved the problem in order of log n, right? But since it is not actually sorted, it is rotated sorted array. We need to we need to first of all analyze like how a rotated sorted array look like. So let us first analyze like how a rotated how a rotated sorted array looks like, right? Let us first analyze it, that how a rotated sorted array looks like. So let's say my initial array is let's say this only, right? I am taking this example only. And one thing more, it is already given here that all elements in A are distinct, which means there are no duplicates. So you don't need to bother about it a lot here, but we will see later why this thing is important for reaching to the optimal solution. But first of all, let's consider on the example first. So let's say that this is our array here, not this one. This is actually a completely sorted array. I need to take this one, rotated sorted array. So let's say like this is our rotated sorted array. So if you see carefully, then you will find that the first element is 4, then we are 5, then 6, then 7, and then it is 0, and then 1, 2, and 3. So if you analyze this structure, what you can see is that this array is actually a combination of two sorted arrays, right? The first sorted array is 4, 5, 6, 7, and then the other sorted half or array is 0, 1, 2, 3. So this complete array can be divided into two sorted halves, right? First sorted half is like this 4, 5, 6, 7, and the another sorted half consists of this one 0, 1, 2, 3. So and so if you just let's draw it. If I just draw it, you will be more clear about how like things go. So let's say we are plotting like this, okay? And let's plot here like these are like indexes, right? 0, 1, 2. As you can see, there are 1, 2, 3, 4, 5, 6, 7. There are 8 elements, so indexes will be 0, 1, 2, 3, then 4, then 5, then 6, and then 7, right? And the elements here are like the first element is 4, so let's also mark it here 1, 2, 3, 4, 5, then 6, and 7, and then 8, right? Let's say like this is our number line. So the first element is 4, right? So 4 is somewhat here. I'm just drawing a rough diagram. And then the second element is 5, so 5 is here, then 6, right? 6 is here, then 7, 7 is here, then 0, 0 is here, then 1, 1 is here, then 2, so 2 is here, and then finally 3, 3 is somewhat here. So if you just join it, like it will form like this increasing sub array, and similarly this will also form another increasing sub array, and can also join it like this. So this is what you can say that a sorted array will look like, and it will first increase, right? Then all of a sudden it decreases, and then again it starts increasing, right? So this is how a rotated sorted array looks like. One important thing to be noticed here is that in a rotated sorted array, right, if the array is rotated by some units, some non-negative unit, or like if it is sorted by some positive units, like if the array is not sorted initially and it has been rotated by some unit, then you can see that the first element is greater than the last element, right? For example, here the first element is 4 and the last element is 3, right? And so 4 is greater than 3, right? So this is also an important feature of this array. So now you know that a rotated sorted array consists of two halves, right? Two sorted halves, right? Like this is the first half and this is the second half, right? So if we can somehow find these two halves, then we can search the element b in these halves individually in O of log n time using binary search, right? So now if we can somehow find these two halves, it would be easier for us. Now one thing you can see, if we can somehow find this smallest element, right? This smallest element, here it is 0, right? If we can somehow get this smallest, or this is also called the pivot element, then it would be we can guarantee that if we can somehow find this pivot element, then all we need to do is to just apply the binary search from pivot to the last index and from the first index till pivot minus 1, because we know that these two halves will be sorted and we can apply binary search on these two halves. So now the problem jots down to finding just this pivot element, right? How we can find this pivot. So if you actually see, uh, we can use binary search to find this pivot. Now let us see how we can use binary search to find this pivot. Okay. So now you know that an interesting property of binary search is that for applying binary search, right? Let's say this is my search space, right? Let's say my search space is low to high. Okay, let's first of all think of when we can do binary search. So if we know that our search space is like this, low to high, and if we are given some value which is in between these low to high, let's say we are given some value, let's call this mid. So if by assessing this mid value, if we can somehow reject either this right half or this left half of the search space, then we can apply binary search, right? So we should be somehow able to reject either this left half or the right half. If we can always do this, then we can ensure that we can use binary search. So now let us see how we can use here binary search to find this pivot, right? So let's say my initial low is like this, which means the minimum index which can be the pivot is like 0, and let's say my highest high index, or you can say high, is like 7. So I know that my pivot will lie in between these 2 points, low to high, right? So if we just take any point in between these two, low to high, then how we can ensure that my search space always contains the pivot? Okay, so let's say if we are given some value, some index which lies in this region, right? So if we know that I am at this left half, then I know that it is never good to go more to the left. It's always better to go to the right. Okay, but how can we check whether we are at the right half or we are at the left half, right? So an interesting property here is that if you if let's say, for example, I'm taking an example. Let's say you are given index 2, right? You are given we are let's say we are given index 2. So, or let's say we are given index 1, or we are given, let's say, index 0, or we are given, let's say, an index 3. As you can see, all of these indexes holds the property that uh, that a of 1 minute, let me write it. uh, Okay, so uh, if you take any index, right, which falls in this first half, right, let's call that index as mid, then it holds that a of mid is always greater than a of 0, right. On the other hand, so this holds when if a of, or you can say that if mid lies in the left half, right. Else else if if let's say if this point, right, let's say if this point lies somewhere in this right half, then what happens that this the value at this index, right, let me let's call this index is here, so the value at this index will always be lesser than the first element. So we can say that else a of that will be lesser than a of 0, and this is an important property, right. So now we know that given any index, we can determine that whether we are in this right half, sorry, whether we are in this left half or we are in this right half, right. So, so this means that we can use. So this means that we can use. We can actually use. We can use. We can use binary search. Binary search. Binary. Oh, sorry. Binary search. Find the to find the pivot. Okay. Now let us take example of this case only, right. So let's take an example over here only. For example, let's say that this is the example, right, and we need to find what will be the pivot. So so initially my low will be like the minimum index, and my, let's say, my high is equal to the maximum index, which will be here 7, right, will be 7. So what we do, we first find the mid, right, and so mid will be what, like 0 plus 7 by 2, which will be 3. And what is the value at 3? So the value at 3 is 7, and since 7 is greater than a of 0, which is 4, so we know that here a of mid is greater than a of 0, right, because what is the value at 3? The value at 3 is 7, and 7 is greater than a of 0, and a of 0 is 4. So which means we are in the right half, right, and if we are in the right half, I need to go to the sorry, which means that we are in the left half, sorry, we are in the left half, and so we need to go to the right, right. And so what we will do, we will just set low to mid plus 1. So now my low will become mid plus 1, which will be 4, right. So the first iteration is completed, and my low becomes 4 and high is 7. Again we find the mid, right. So mid will be like low plus high by 2, so it will be 4 plus 7 by 2, and that will be equal to 11 by 2, that will be equal to 5, right. Again we compare, so we see that a of 5 is lesser than, right. So a of 5 is lesser than, a of 5 is 1, and 1 is lesser than 4. So it means that we are in the right half, because we are already, I have already written this, that if a of mid is lesser than a of 0, it means that we are in the left half. Okay? And if we are in the left half, which means that uh, my pivot will lie either at this index or to the left of it. So I will be having initially also pivot, and let's call it to be initially 0. So since a of mid here is lesser than a of 0, so I will simply set my pivot to mid, and I will just reduce my range. I will just try to check more values to the left in order to check that whether pivot can lie more left or not, right. So I will just set my high to be mid minus 1, right. So now after doing this, uh, my low will be 4 and high will be equal to mid minus 1. So mid was 5 and high also becomes 4. right? 5 minus 1, mid minus 1, so it becomes 4, right? So as soon as I get low is equal to high, it means I have found my pivot, right? As soon as low becomes equal to high, it means that I have found my pivot, right? So if low is equal to high, it means I have found my pivot, and so I will just simply break. Okay, so now once I have found my pivot, so I will simply apply binary search. I will simply apply binary search on like two halves. The first half will be from 0 to pivot minus 1, right? And the another binary search I will apply on pivot to n minus 1. And whichever range returns me a value which is not minus 1, I will just simply return that value. Okay. For example, here I will apply binary search from 0 to 3 because pivot is 4, and from 4 to 7, right? And for applying binary search, you can either write the standard binary search algorithm like setting low and high, and then each time calculating the mid and checking whether this value is greater than the value to be searched or lesser than that. Either you can do that, or there is also a function in C++ that is also called binary search, which can also do your job. So basically you can also use, there is a function in C++ named binary search, right? And basically it accepts an iterator to the left index, or you can also call lower index and second one is iterator. But yeah, binary search returns not a value, it just returns a boolean value whether it is present or not. So it's better to write your own algorithm on binary search, whether it will exist in this half or to find the value in this left half and the right half, and whichever returns the value you just simply return it. Okay, so that's the thing. Now once we found this, like we need to apply binary search on 0 to 3. So if we apply binary search on the range from 0 to 3, searching for 4, we will find that the element is present at this index, which is 0, and so we will be returning 0. Okay, and if it did not if it haven't contained this element 4, then we would have to apply the binary search on the right half. Okay, so the overall time complexity in this case will be order of log n. Why? Because we are just spending O of log n time to find the pivot, right? We are using O of log n time to find the pivot, and also O of O of log n times to find the element in the left and right halves each, right? The overall time complexity will be O of log n, right? Although actually it will be order of log n plus log n plus log n, right? 3 times log n, but yeah, asymptotically that will be order of log n only. And since we are not using any extra memory space, so that will be the so the space complexity will be order of 1. Okay, so the space complexity will be order of 1. Okay, so this was the problem about searching some value in rotated sorted array. Now uh, if you want, like we can do a quick pseudocode of this also. So let's see the pseudocode. So in the pseudocode, let's say we have some function which is that find, right, find index, call this find index, and let's say it accepts an array, right? The size of the array, let's call it n, and the value to be searched, let's call it b. Okay, and so first of all, what we will do, we will first of all have some pivot. So pivot will be, let's call it find pivot. So first of all, we will just find the pivot in this array, and then uh, let's call let's call let's have some variable, or let's store the index. So so now once we found the pivot, we will just apply binary search in the left half. So we apply binary search in the left half, right, and from 0 to pivot minus 1, right, we apply the binary search in the left half, and we check like if index is not equal to -1, I just simply return this index. Otherwise we store the index by looking what will be the, now we try to search in the right half, so we just do binary search in the right half, and the right half consists of elements from index pivot to n minus 1. We pass the array, right. We again check if this is not -1, which means there is an element in the right half, so we return that's index. Otherwise we don't found if we don't found that element in the left half as well as in the right half, we simply need to return minus. Okay, so so this will be the pseudocode, and now we need to implement this function find pivot. So let's implement this. So this called uh, find pivot. Okay, so this will accept an array, then n, then, and that's it. So for finding the pivot, what we do, we maintain two things. The first one will be the low, which will be the minimum index where the pivot can be, and the another thing will be high, and this will be equal to the maximum index where the pivot can be. And uh, and what we do is that uh, we also have something, and we also have a pivot. Initially it will be 0, right? So now what we do, we just write this standard algorithm, like while low is equal to high, while my search space is not empty, I first of all find my uh, mid value, that will be equal to low plus high by 2, right? And then I just examine this mid value to know whether we are in the right half or in the left half. So if the value at the mid, right, it is greater than the element at the beginning, then this means that we are in the right half. We are in the right half. It means that we are in the left half. It means that we are in the left half. So but we know that the pivot will be present in the right half, not in the left half. So I need to go to the right, right? So I need to set my low to mid plus, okay. And if it is not so, then it means that i am at the I am at the right, I am at the right half, and I need to go to the I need to reduce my search space towards the left, so that I can check the possibility of having the pivot more to the left or not, right? So one thing I can do, I can just set my pivot to mid, and decrease my high to mid minus 1, high to mid minus 1, right? And at the end I will be just returning this pivot element. Okay, so this will be the, actually let's call it return to int here also. So this will be the pseudocode, right? So yeah, that was all about the problem rotated sorted array search. But yeah, one thing more, uh like uh this problem is basically about searching a value in a rotated sorted array provided that all the elements are distinct. Okay, but what if all the elements are not distinct? Means that we allow some duplicates. So if we allow some duplicates, actually this solution may not work in that case. Why? Let's see at the structure of how this rotated sorted array will look like if we allow some duplicates. Let's see. So I am again using this drawing. So let us see. Okay, so let's say, okay, so so if we allow some duplicates, then my rotated sorted array might look something like this. Okay, might look something like this. That let's say increase some point and it having like this, and then okay, yeah, okay. So my sorted array might look something like this. Okay, so now you can see the pivot is over here, right? The pivot is over here, and this is my left half, and this is my right half. Okay, but let's say our mid value at some point of examining the search space, we got some mid value. Let's say my mid value is here. Okay, so now what we will do, we will just compare this value with this starting value, right? But as you can see, the starting value is equal to this this value. So now we cannot determine, actually we cannot exactly say that whether we are in the right half or we are in the left half. Okay, similarly, let's say if the mid value where at comes to be some point at here, right? Then again you examine that, okay, this point is equal to this point. This point, the value at this point is actually equal to the value at the beginning of the array. Again, you cannot say with accuracy that whether you are in the right half or you are in the left half. So from here, what we can see, or what we can say, is that this algorithm, you can say this algorithm, uh, or you can say, if if duplicates are allowed, if duplicates are allowed, then this will not work, right? Because then this will not work. Okay, this will not work, and the reason why, so you might think of why this will not work, like I have already explained you. This is because that it is undeterminable. It is undeterminable in some cases to say whether, to say whether we are in the, we are in the left half, in the left half, or we are in the, or we are in the right half. Okay, so that's why in that case, if duplicates are allowed, then we cannot actually use binary search like we did above to find the target element. So in that case, there is only one way of finding that element, and that will be linear search. We cannot use binary search like this in that case. Okay, so just keep this in mind, that it works only if all the elements are done. Okay.